Okay. First of all, I would like to thank the organizers for giving me the opportunity to give this presentation and being here. So you just saw, in fact, this beautiful representation of the measurements, the observation by the LIGO and Virgo collaboration that over the last 9 years have observed of the order of 90 coalescences, plus we have a few tens of observation from independent analysis. And this plot here represents the black holes in blue. The neutron stars are in orange. Just a few highlights. The very first detection of a merger of two black holes, the first binary neutron star, the largest binary black hole observed so far, the 21st of May 2019. Here you see one particular event. Actually, two were observed where the mass of the secondary it's perhaps too small to be a mass of a neutron star, and too large to be the mass of a neutron star, and too small to be the mass of a black hole if the black hole forms from a collapse of stars. And then I wanted to highlight a discovery that came out during the last run, the ongoing run, of a neutron star black hole detected at 29th of May 2023. The LIGO and Virgo Kaga detectors are going through a new run, which is called O4, and during the last year have announced 105 signal candidates. So in this brief presentation, I will describe at the beginning the role of the waveform models in the detection and interpretation of the results. The important fact that was highlighted also by Zibern this morning, that with more sensitive detectors and observational runs, we would need more accurate waveforms, and how scattering amplitudes and wordline methods may help to address this important accuracy challenge. And I will show you some very encouraging, I think, results that we obtained recently for bound orbit waveforms and scattering by informing the effective one-body approach with post-Minkowskian results. And in fact, what I'm going to tell you is based on two papers that came out just in the last few months, done with the following people, Gustav Jakobsen and Gustav Mogul. Gustav Mogul is here, and two graduate students, Raj Patil and Lorenzo Pompili. The bottom line is that we have a model that generates waveform where the conservative information from the post-Minkowskian results are included. And you see here the waveform for some values of the parameter compared with numerical relativity, which is in black. Okay, so first of all, why we need waveform? We need waveform to extract parameters. From the frequency evolution, we infer the masses of the binary. From the amplitude in the masses, we can infer the distance. From the time of arrival of the detector, of the waveform at the different detectors, the amplitude and the phase, we can reconstruct the sky location. If we see this kind of modulations, we can know whether the binary was moving on a circular orbit or eccentric. We just heard from the talk of Misha Ivanov that if we compare, for example, the binary black hole waveform with matter, because there is a neutron star, we can shed light on the internal structure of the neutron star. And finally, we can also build waveform. This is happening actually more in the last few years in so-called alternative theory of general relativity, and we can probe the theory of gravity. So in order to do all this, we have to solve the two-body problem in general relativity, which means basically we have to solve the Einstein equations. And the best tool at our disposal is to do it numerically on supercomputers, but this is very time-consuming. To produce 15 orbits of two black holes going around each other, it may take between a few weeks and 6 months, depending on the parameter of the binary. So numerical relativity is restricted to a certain region here of the parameter space. Then we can also solve the Einstein equation in approximate way, perturbatively. The oldest method is post-Newtonian theory, where everything is expanded in powers of V over C or GM over RC square. Of course, you are very much interested because many of you are contributing in the post-Minkowskian expansion of the Einstein equation, which differently from post-Newtonian does not expand in the velocity, and so could be particularly important not only for scattering, but also for high eccentricity. And we can expand the Einstein equation in the mass ratio. So this will be strong field, no expansion in velocity, or in the weak field. Then on one side, we can put this method together in the effective one-body theory, which here is an example of the waveform in time domain, which has also a physical answer for the mergering down, which then can be made more accurate with numerical relativity. On the other hand, we can build also waveform in a frequency domain. They are called phenomenological. They are built fitting effective one-body, post-Newtonian, numerical relativity. And this happens because actually if you plot, for example, the frequency, the amplitude of the wave as a function of frequency, or the first derivative as a function of frequency, they are very simple functions. Okay, so one slide about how we put together the analytic and numerical results to build a waveform, because I will use it later on when I will go into more details about how we incorporated the post-Minkowskian results. So in the context of the effective one-body theory, what we do is that we start with a waveform which is not calibrated to numerical relativity. We include higher order corrections to reduce the difference with numerical relativity until they agree very well. And in the most recent development of this family for the ongoing run, 441 numerical relativity waveforms were used, where this process is done for each point here in the parameter space. This is the binary effective spin, and this is the mass ratio. The different colors correspond to different mass ratio of numerical relativity waveform from the SXX collaboration. The waveforms are used for the template bank. This is a projection of the template bank used by much filtering searches at low masses. Post-Newtonian templates are used, and the high masses effective one-body ones. And besides the SOBNR, let me say again, we have the IMR phenom waveform in frequency domain, TOB RISAM S, and other EOB waveform in time domain. And then where we have numerical relativity, we can interpolate directly numerical relativity and build so-called numerical relativity surrogate models. Okay, so this is, as I said, ongoing runs for LIGO and Virgo and CAGRA. And of course, there will be also the next runs of 5 starting in 2027 and further upgrades. But let me say that we expect in the next decade to have a more sensitive detector, Einstein Telescope and Cosmic Explorer. They will increase the sensitivity, which means the range at which we can see binary black holes will be much larger, large redshift, as you can see here. And also this detector will go more at low frequency, which will allow to bring in band black holes with larger masses of the order of 1,000 that we cannot see today because they merge outside the bandwidth of the detector. That's why we are seeing black holes of a few hundred solar mass at most. Now, it's quite overwhelming to think at the number of events that this detector will have. In 1 year, we could have 10,000 of binary black holes detected with a signal-to-noise ratio larger than 100. This is a factor 10, more or less, more than what we can see today. And then the next decade, we will have LISA in space. It's a mission which has been just adopted in January by the European Space Agency, which means is now under construction. And LISA will see different kind of sources, and in particular, the merger of black holes at the center of galaxy. You see here the noise spectral density of LISA and the tracks of binary black holes with different masses, as you can see here, with very large signal-to-noise ratio. In fact, the signal will be much louder, and they will last for weeks and months, very differently from now. So now I want to give you an example, actually 2 examples, why we cannot use the current waveform model with these future detectors. The first one, I take an event like the event which has this large mass ratio 10, which was observed with the puzzling companion I mentioned at the beginning, but now highly precessing. And we considered one state-of-the-art waveform model from IMR phenom and another one from SOBNR. One is used for the signal, which is injected in the data, and the other to recover. And we are interested in cosmology. We want to measure the Hubble-Lemaitre parameter, which if you measure the distance, and you can also localize the source in the sky, you can get the redshift, then you can basically measure the Hubble-Lemaitre parameter. And we do it with different runs of 5, the next run, an upgrade of it, and Einstein Telescope and Cosmic Explorer. You see the large signal-to-noise ratio. This is what we find. The true value is here for the luminosity distance, and this is what the posterior distribution using the other waveform model would say, and the localization in the sky, this is the galaxy, is completely off. So due to systematics, we would get the wrong Hubble-Lemaitre parameter. The last example, let's consider LISA, which was mentioned at some point as allowing us to do tests of general relativity like quasi-normal modes. And in this case, what we did was to inject a numerical relativity waveform, so the best representation of the waveform we have today, and we recover it with a parameterized model, an SOB NR model, which allows us to extract deviation from the quasi-normal modes of general relativity. So if general relativity is not violated, this two-dimensional posterior distribution should be here. And so due to systematics, again, we will have a false deviation from GR in the quasi-normal mode, the dominant one, during the ring down. So this is not good. So the accuracy of the current waveform model will need to be improved, as several papers have shown, by 2 orders of magnitude. And we need to improve also the numerical relativity simulation because we use them to calibrate the models. And moreover, until now, all the waveform models used by the LIGO and Virgo and Kaga collaboration have been tuned, have been focusing on quasi-circular orbits. But we need to include all possible effects, including generic orbit, eccentricity. The binary could be in an accretion disk. It could be perturbed the motion by a third body that is around. Moreover, there could be gravitational lensing, which also can change the waveform. So if the binary is here and there is a lens between it and where we measure it, the waveform will be modified. The unlensed waveform here is in black. The lens waveform is in color. By the way, I see a bit of blurred. I don't know if it is me or not seeing, or it's maybe it's not me. Okay, so in order to address this problem, we have to push post-Newtonian, post-Minkowskian GSF at higher order, combine them in the UV approach in a more efficient way, and also we need to develop more efficient way to calibrate numerical relativity, because until now we are not even going, we are not producing models that are at the level of the error of numerical relativity. So there is this wonderful community, you, that have decided actually to help us in tackling this problem. And in fact, we expect that your tools will be particularly important to tackle the frontier of gravitational wave modeling, which is the eccentricity. What you see here is a visualization of an eccentric binary, which you barely see actually the 2 black holes going around here. This is the flux of radiation. And you see here the waveform, very complicated, because each time also the 2 bodies come closer at the periastron, you have a burst of radiation. And so this is the problem we have to address. And because the post-Minkowskian approximation is more accurate than PN for scattering encounters at large velocities, this means basically like if you fix the periastron distance, you expect that if you increase the eccentricity, post-Minkowskian will be better than post-Newtonian. So let me now explain what we have done in these 2 papers that I mentioned at the beginning. So first of all, what is the effective one-body approach? It's an approach that maps the 2-body dynamics in a one-body one, which is the one of an effective body moving in a deformed black hole spacetime, where the deformation parameter is the mass ratio. So the symmetric mass ratio. This nu is the reduced mass divided by the total mass. So it ranges between 0, the probe limit, and 1/4 when the 2 bodies have equal mass. So the key idea is basically you want to do perturbation of the Einstein equation and radiation, better not to expand the Schwarzschild or Kerr solution. Basically, this is the main idea of the model. So it provides a new Hamiltonian, which is related to the effective Hamiltonian through this mapping here. So let me show you, actually, sorry that the colors don't come out very well. So this effective Hamiltonian in the non-spinning case, let's consider non-spinning case, has a potential here. So this potential, you all remember this potential, A, which in Schwarzschild is 1 minus 2u. And now it gets correction if we use the post-Newtonian approximation that depends on nu. And these corrections are known today up to 4pn. And what is not known is the 5pn. Everything that is in Sion, which however doesn't show up very well in these slides, is going to be a calibration parameter. Okay, so I'm showing you the potential post-Newtonian expanded because this was historically the way in which the model was built, using post-Newtonian results. And I want to show you the shape of this potential divided by r squared as a function of r. You might remember in your course of general relativity that this potential in Schwarzschild has a peak at the photon orbit, and it varies very smoothly after one applies a Paderi summation when you change the mass ratio. So here is the probe limit, and here is mass ratio 1. Okay, so what we did was to use the information from Post-Minkowskian theory, the conservative results until now. We complemented them also with the post-Newtonian results because we are describing bound orbits, and at a certain order in PM, we are obliged to do that. So the effective Hamiltonian with spins, because this is done, the work we have done includes also spin, is now more complicated with respect to the one I showed you before. So these are the gyro-gravitomagnetic coefficients that multiply the spins. So these A plus, A minus are just built from the single spins of the two black holes. So you have this term here. Then again, the potential now is not in Sion, so you can see it. And the potential has this structure, so it's a deformation of the Kerr potential. The B factors are exactly the one in Kerr, while here we get a correction that depends on the symmetric mass ratio. Like also the gyro coefficients get a correction that depends on the mass ratio. So as I said, we use results from the literature, which have been obtained in the last 5 years. The results at 1 loop, 3 loops, and also 2 loops, 3 loops. 4 loops we have not included because they are not complete. And in this table, whatever is in color means they have been are known. This row here is basically the one of the spins, and this is non-spinning, this direction here. Now notice the powers in G. So we use in our paper a new way, we call it physical way of referring to the post-Minkowskian results. So when I say we are 4pm, we are along this diagonal, which is G to the 4th. When I say 5pm, we are along this diagonal here, where of course the non-spinning is missing except for these results in this paper. Okay, let me go a little bit more in details. What are these deformation parameters here? So they have a contribution that depends on the even in spin PM corrections here, and this is odd in spin in the gyro, okay? And this term here is there because, as you know, starting from 4pm, there are tails effect, and today, for bound orbits, the Hamiltonian at 4pm is not known, and so we had to basically add however, 4pm corrections such that when we expand the Hamiltonian, we can recover at G4 order all the PM corrections that are known. So we are obliged to do that. So how do we do this? How do we compute the coefficient from PM? Well, we compute the scattering angle in the effective one body. Just we invert this relation with respect to PR, and then through this integral, we get the scattering angle, and then we match the scattering angle to the one computed in PM, and we get all the coefficients. So again, these coefficients here and the one of the gyro are given, in very simple expressions here, although these coefficients are quite complicated. This alpha. These alpha are function of gamma, which is just E effective divided by mu, and they are function, of course, of nu. Now, not surprisingly, all these coefficients, because the PM results depend on logarithms, the logarithm, the logarithms, elliptic function of the first and second kind. So now in our Hamiltonian, we have all these expressions. Okay, so now what do we do with our Hamiltonian? Well, we take the Hamiltonian, we build the Hamilton equations, and we complete the equation with radiation reaction force so that we have dissipation. We are not including any post-Minkowskian results in the dissipative radiation reaction force here. We use what is known today resummation of post-Newtonian and gravitational self-force. And we do all this work in a Python code that we have developed in the last few years for our work in the LIGO Virgo and Kagra collaboration. And so what we get is that we get the orbit, okay? So I show you at the beginning a waveform. I'm now showing you how we build that waveform actually. So using the parameters for that waveform there. So this is the trajectory. This is the evolution of omega, the orbital frequency. We reach a peak at the light ring. And how do we complete the waveform? That you will see in a moment. But there are very interesting results just looking at the in-spiral. So I have the in-spiral, I can compute the binding energy. And the binding energy can be computed with radiation reaction effect or only for strictly circular orbits. And we compare the results with numerical relativity. Numerical relativity here is in dashed for different mass ratio. This is one cycle before merger. If you use only strictly circular orbit, they go away, I mean, they deviate from numerical relativity quite soon. But if you include the radiation reaction, you can see that they follow quite well numerical relativity. Numerical relativity error is very small. You can see here, okay? It's the gray region here. So even up to one cycle before merger, the agreement is very good. And the agreement is very good also with the model that actually we calibrated for the LIGO Virgo run, which is called SU-BNR V5. However, this model, it's actually, yes. However, this model, we calibrated the 5pn terms to numerical relativity. So what is actually striking here is that using only post-Minkowskian information for the in-spiral with no calibration to numerical relativity, we can achieve a result which is very close to the one obtained by calibrating the post-Newtonian results. Let's switch to spin. So you can also extract from numerical relativity the spin orbit contribution, which are now here in black. Again, as a function of V and one cycle, gravitational wave cycle before merger. And it's quite nice to see how adding the spin effects from 2pm, 3pm, 4pm, 5pm, you see the agreement becomes better and better with numerical relativity. Again, contrasted with the best PN model that we have today, SU-BNR V5, which is now calibrated also in the spin sector. The agreement of post-Minkowskian is still very good, comparable. And for spin square contribution, again, we extract them from numerical relativity. This is the dashed black line with the gray region, which is the numerical error. And also here, the agreement of SUB 5pm, it's again very good up to one cycle before merger. And this is just an artifact of the crossover, crossing zero, because this is the modulus of the difference in the binding energy. Okay, very good. So now let me tell you about the waveform, because this is just the binding energy. So I wrote before the equations here. So we have the polarization, we decompose in modes, and we have to complete the waveform. So in the in-spiral plunge, again, we are not using result from post-Minkowskian until now. This is just a resummation of post-Newtonian and gravitational self-force results for the 2-2 mode. We compute the 2-2 mode on the trajectory that I showed you before, and we get basically the waveform. We get the waveform up to more or less the peak. This is the gravitational wave frequency that goes up, and then it flattens at the quasi-normal modes, which is here. How do we complete it? We add a function. Again, the Sion here are a problem. For the mergering down, we use the quasi-normal mode, the dumb sinusoid, and the function that depends on time, which is tuned to numerical relativity, to obtain basically the full gravitational wave frequency and the full waveform here. So at the end, the waveform basically is in spiral plunge before the peak, and then mergering down after the peak. But this is the way in which the full waveform is built. Okay, so now we have the waveform from Post-Minkowskian, using the Hamiltonian from Post-Minkowskian. We can tune a little bit to numerical relativity. And the only thing we tune, let me go back a moment, is this is basically the time where the peak of the waveform is with respect to numerical relativity. So we do that, and we tune it to numerical relativity. And in order to assess how well the waveforms are, we compute a quantity, which actually is not an amplitude, M. I realize it's the same symbol you use. It's called the mismatch. It's 1 minus the overlap between numerical relativity and the model. The only thing you have to know is that when the mismatch is small, it means that the model agrees very well with numerical relativity. So let me show you the result. This is the fraction of cases which have a mismatch smaller than a certain value. And SUBNR PM with only tuning delta TNR, this time to merger, is the blue here with the median here. And the model V5 based on PN, only tuning delta TNR is in orange. So it's better than the model based on PN. In green is the model when you calibrate also the non-spinning and spinning sector for V5. So just to understand better what is causing this difference, mainly, if we plot the mismatch as a function of the spin, the blue becomes worse when you go to larger spins. And this means basically we need to improve the Post-Minkowskian result in the spinning case. So I have only 2 slides and I'm done. So I want just to have one slide about the other work that concern the prediction for the scattering angle, not the waveform, using Post-Minkowskian theory and the effective one-body. So here, one important difference is that the coefficient in the Hamiltonian that I was showing you before that are obtained from the scattering angle did not include the dissipation, because the dissipation is included through the radiation reaction that enters the equations of motion. But here, the deformation coefficient depends on the dissipative terms. So this is a plot on the left that shows the scattering angle for a certain value of the energy compared with the numerical relativity in black as a function of chi plus. For these 2 models, the WPM model was introduced last year by Damour and Retegno. And the difference with our model is basically the deformation and the fact also with respect to the spacetime, the black hole spacetime, and the fact that in WPM, you don't recover in the non-spinning case the probe limit actually with that deformation. You can appreciate a very good agreement with numerical relativity, although you can see some degradation going to large positive spins and also negative ones in the region of strong field when the deflection angle is quite large. And this is computed at 4 p.m. Again, think about the diagonal in my plot before. Now, if we do the same at 5 p.m., which is however incomplete because we don't have the non-spinning part, we have more degradation with numerical relativity, which means that we really need to have also the 5 p.m. results. Okay, let me now conclude. So I said that to correctly interpret the gravitational-wave observation, we need to improve this waveform model. I gave you 2 clear examples in cosmology and test of general relativity. We need to push the perturbative calculation at higher order, but at the same time, we also have to combine them in maybe novel way and more effectively in the effective one-body approach. I show you the first in-spiral merger in down waveform that use Post-Minkowskian calculation, the quite remarkable agreement of the binding energy without doing any calibration of the model. And then for the waveform, just calibrating this time to merger, we can get a performance that is better than the state-of-the-art SUBNR model, which is based on PN. The last point is the future. Maybe that's actually the most important thing. So we would like to resum this potential and gain more accuracy with NR. We need to do a full calibration to numerical relativity, which we have not done until now. We would like to include the Post-Minkowskian results also for the radiation reaction force and gravitational modes. But for what I understand, they are not available today at very large Post-Minkowskian order. Extent to eccentricity, where perhaps we will see even more advantage of Post-Minkowskian theory. And then, of course, use new results as they become available. In particular, we are looking forward for the 4 p.m. maybe being completed for bound orbits, and perhaps also the 5 p.m. And thank you for your attention.
Thanks a lot, Alessandra. We have time for maybe 1 or 2 quick questions. Lance?
Thanks for a great talk. A question about eccentric orbits. What are the astrophysical situations where you expect to get them, given the circularization from radiation?
Yeah.
So are there NR results that you would need to calibrate that regime?
Yeah, so first of all, yes, there are, people in numerical relativity have started to produce numerical relativity waveform with eccentricity. Also, we have first models with eccentricity and spin effects, but not yet spin precession. So about the astrophysical expectation, indeed, it seems that until now, the majority of the population we are seeing is well represented by quasi-circular orbit. But there are scenarios for the formation of the binary where the binary forms through dynamical capture and not from, it's not a binary with initial, start and then collapse supernova and then they form the black holes. So if this black hole form in globular clusters, so dense regions with many stars, so then this means that they could have, they are captured, and then there is not enough time to circularize from that time to the time in which they enter the bandwidth of the detector. And in fact, people really are looking forward to this eccentric waveform because that's a way of perhaps discriminating or finding a subpopulation of black hole, binary black holes of this kind, which I think is very important for people working in that area.
Yeah, thanks for great talk, Alessandra. My question is, now that we provide the 5 p.m. 1SF conservative result, I mean, would that be also not interesting?
Sorry, could you repeat the...
That we provided the 5 p.m. 1SF conservative result.
So the fact is that, so until now, so they are, linear in the mass ratio, but of course they are truncated in PM, right, at 5 p.m. So, for example, we have built this FFT1 body with the gravitational self-force results, which are, exact at linear order in nu with no expansion. So we should try. I mean, I'm not saying that we should try, but what I'm saying is that we are adding a term which is partial, right? Because it's truncated at 5 p.m. and is linear in nu. So it's a mixture of, and is not complete in any of the directions. But, we should try and see what we find.
Yeah, maybe so that everybody could get their lunch in time, we can thank Alessandra
Yeah.
once again for the